Okay, so now we're going to start talking about STL iterators. Up to this point, we've covered the C++ function templates and class templates at some length. We've gone through the various STL sequential containers that are important to understand, things like vector and dec and list and so on. And now we're going to start diving into STL iterators. You've already seen bits and pieces of iterators in earlier discussions, but now we're going to do a real full-blown discussion of this in great detail. So what is an iterator? Well, first of all, an iterator in C++ STL is just a C++ version of the so-called iterator pattern from the Gang of Four book. And we'll be talking more about patterns later in the course, and we'll be talking more about the iterator pattern later in the course. But for the time being, this is a diagram that shows the iterator pattern. And so you can see here it's got a couple different roles, a couple different pieces. Most importantly, you have this thing that creates the iterator, and that's called an aggregate in the STL model. In our world of STL, that of course is a container. A container is got a factory method, a couple factory methods, actually about 8 factory methods that make iterators, either the beginning part or the end part. And then there's also the iterator interface itself. And we'll talk a lot about that because that's really very important to understand to make any sense out of STL algorithms, is to understand the different categories of iterators. So we'll talk more about the pattern later, but the key point is that someone's thought about this for a long time and it's been documented in the form of a pattern. What this pattern does is it allows client code, applications, or code that's using the iterator pattern, as opposed to code that's implementing the iterator pattern, to access all the elements in an aggregate in a container sequentially without exposing any underlying representation. So as you can see in this very simple example, we have an iterator, and we're going to have it be an iterator to a vector. We get the beginning to the iterator from using the factor method called v.begin, and we're going to march through this from beginning to end, and every step along the way we're going to print out the contents of the iterator, of what's pointed to by the iterator, and until we reach the end of that range. So we go through each one of these things sequentially, and it doesn't expose the internal workings of the vector in any way, shape, or form, which is cool. The iterator object itself encapsulates the internal structure of how the iteration actually occurs. So this is just a little snippet of an implementation that could be used to create an iterator for a vector. So if we have a vector, then nestled inside there somewhere could be an iterator implementation. And there's all kinds of ways to implement this, by the way. And this is just kind of showing how we're able to leverage the implementation of the vector to implement our iterator. And so the iterator implementation encapsulates the structure of the iteration. And we'll talk more about this stuff. If you want to see more about this specific example, take a look at the stack, the code review Stack Exchange link down below, where a person has created a nice iterator to show sort of how it works. And we'll be looking at those kinds of things ourselves later in the course. But the key point there is that the iterator shields the client applications, most typically the algorithms, from knowledge of how the containers are implemented under the hood. You can think of an iterator as essentially being a generalization of the C and C++ concept of a pointer. So hopefully you're familiar with the concept of a pointer from a data structures course like 201 that we teach at Vanderbilt. And basically an iterator points to another object. So an iterator points to something. And just showing this as a very simple example, the iterator operation dereference, which is operator star, what that does, as you can see here, is it actually points to a vector. And when you dereference something, it follows that pointer, gets the vector, and then uses the subscript operation to get the actual element that's being referenced at that moment in the traversal through the state of the underlying vector. And if you look carefully at this implementation, the way the iterator is implemented is it's going to keep a pointer to a vector and then an index, and it's going to increment that index as it goes through the vector, as you iterate across or traverse through the vector itself. Iterators are often used to iterate over a range of objects, and that's really at the heart of what STL algorithms are all about. So you can see here we have the famous copy algorithm, which is a great way to demonstrate lots of different properties of iterators because it's very simple and yet it's very powerful at the same time. And you can see here that copy works on a range from first to last, which is the input range, the input sequence that we're iterating over. And then it also has an output iterator where the result is going to go. So you can see we're iterating over the range of the contents, say in a vector or a list or a deck or whatever we're iterating over. If an iterator points to one element in a range, then you can increment it so that it points to the next element. So you can see here in the copy algorithm that as we go through this range, every time we copy one element from whatever the current first item is pointing to into whatever the current output iterator result is pointing to, after we do that, we increment the iterators by one. So first gets incremented and result gets incremented. So those things get plus plus. And of course, if this is mapped to various containers in STL, those will be overloaded plus plus calls. If this is actual pointer arithmetic on a built-in C style array, then plus plus will simply be incrementing a pointer. But in either case, this code is identical whether we're iterating through iterators that are part of an STL container or a user-defined container, or whether we're iterating over things that come from native arrays. That would be more of the C style way of doing pointer arithmetic. Iterators are very, very important for generic programming because they provide the interface or the connection between containers and algorithms. So if you take a look at this example, you can see that we have a couple of containers, vector v1 and vector v2, and we've got the copy algorithm. And as you can see here, the way that those things are connected is not by having copy take in a vector, but instead copy takes in a range from beginning to end. And that is more powerful for a whole bunch of different reasons. It makes it easy to write generic code, but more importantly, it gives you more flexibility over what you pass in, because you might not want to pass in the entire vector. You might want to pass in the first half of the vector, or from the third element to the third to last element, or whatever. And by having the algorithms work on iterator ranges, it gives you a lot more control over what you can pass in and what the iterator range is, and then of course what the algorithm will do, what the scope of the algorithm will do. So containers only need to be able to provide access to their contents via iterators rather than having the various algorithms know specifically about the properties of a given container, which is again much more generalizable and much more flexible. One of the consequences of this is you can have nice mix and match like properties. You can see here that we have a vector of int and a list of int, and yet we can still use the same copy algorithm on both of these things because it doesn't know anything about whether it's a vector, doesn't know anything about whether it's a list or a deck or a set or a map or whatever. Instead, it just knows how to walk through this range using the iterators that we see defined down here. So that's much more flexible, much more generalizable. And again, if you think about the philosophy of STL, it's about mix and match, plug and play, orthogonal ways of combining various elements without having to have a lot of unnecessary restrictions placed on them beyond just a few simple things like what's the iterator category. So it turns out that there's 5 different types of categories of iterators in STL: input iterators, output iterators, forward iterators, bidirectional iterators, and random access iterators. And this is going to be really important to understand what's going on with STL, so we'll talk more about this shortly. As examples of these things, there's providers of such iterators. There's an input stream or an iStream, which can be used as an input iterator when properly adapted. There's something called an OStream, which can be used as an iterator when properly adapted. There's forward iterators. None of the containers that come with STL, I take it back, there is one. Forward iterators are required for forward lists. And then there's a bunch of containers. In fact, the bulk of the containers in STL take so-called bidirectional iterators. So things like regular list, which is implemented as a doubly linked list, so you can go forwards and backwards with equal ease. Set, multi-set, map, multi-map. Those are all bidirectional iterators. And then the final category, which is the most powerful one, is the random access iterator. And there are examples there like vector, dec, and an array, a built-in array. So the consequence of this, of doing things like this, is it allows us to be able to have algorithms that work seamlessly on both either built-in arrays, C style arrays, that use pointers and pointer arithmetic, or user-defined or STL-defined iterator types like list or vector and so on. And so this is just a simple example illustrating how you could do this to basically have an array that's an array of ints, a built-in array of ints, and then we could go ahead and make a list that's the same size, and then we could copy the contents of the array into the list. So what we're going to do now is just quickly show the relationship between the different iterator categories. We have the input and output iterators, which are the kind of the base of everything, and they're the most basic type, and we'll talk in a second about what differentiates them. In a nutshell, input iterators can only be used to read something, and output iterators can only be used to write something. So that's why they're input and output iterators. And then the other three types of iterators all kind of conceptually inherit the properties of the iterator before them. So a forward iterator is both an input and an output iterator, so it has the ability to read and write, but only in one direction, only from sort of left to right. And a bidirectional iterator is something that's got the ability to go from left to right and right to left, so it can go bidirectionally. So all bidirectional iterators are forward iterators plus some extra stuff. And then finally, we have the pinnacle of iteratordom or iteratorship, which is random access iterators, which are bidirectional iterators that have the ability to move around randomly within the contents of the container or the underlying array that they may encompass.